All right, so let me summarize the steps you're going to need to take in practical examples in order to use the variational method. Okay, so remember, our inputs are going to be, you'll be told what kind of quantum system we're talking about. Is it a particle in one dimension, or is it a collection of spins? And you'll be told what is the Hamiltonian for that system. Okay, and so step one is choose a trial wave function with some arbitrary parameters, or actually more generally a trial state. Okay, so we pick some state. In a spin system, it wouldn't be a wave function. It would just be some parameters that define our state in terms of our basis elements. In a particle system, we might be choosing a wave function. Okay, and what we want to do is not just try one wave function or one state, but it'll be better if we can try a whole family of states by choosing a state that depends on some arbitrary parameters. Number two, we want to normalize that. Okay, so if we just write down a wave function, then it won't necessarily be properly normalized. But we could always multiply by a constant and choose the constant so that the wave function will be normalized. Assuming that is that we've chosen a function that actually is normalizable. Okay, so you want to make sure that the integral of the square of your trial wave function actually is less than infinity. Okay, so now we've got a normalized state, and we can check that by evaluating the inner product or the integral of the wave function squared, and that should be 1. Step 3, we're now ready to calculate the expectation value of the Hamiltonian. Okay, so I'm going to call this E phi of A. A are the parameters that my state depends on, and so E is the expectation value of the energy for that state specified by those parameters. Okay, and so this is going to be something where if it's a 1D particle system specified by a wave function, we'll have to do some integrals. Or if it's just a spin system, then we'll have to maybe evaluate various inner products. Okay, so now we've got this energy expectation value which depends on the parameters A, and so we know that whatever parameters A I choose, then this E is going to give us an upper bound for the actual energy. And so now what we want to do is figure out what is the best out of all those upper bounds. And so we'll take our function E as a function of A and then try to minimize that over all the parameters. And so to do that, you're going to be doing some calculus. So let me just remind you that what we want to do is require that, d by dAi of our E phi of A, that has to be equal to 0 for a minimum. Okay, and so that can be that could give us several equations that we're going to have to solve. Now, sometimes you won't be able to solve those equations, and in that case, what you'll want to do is some kind of numerical minimization. So in complicated situations, in actual applications, then we actually want to use some numerical algorithm to try to minimize this function. Okay, and so let's say we've done that. So then the conclusion is that our minimum value, whatever it is, that gives us our estimate. It's an upper bound, but we think of it as some way of estimating what the ground state energy is. So that gives us our upper bound for E0, and that's our result. Okay, and so just a couple of things. If you want to do as well as possible, then you want to try to consider as general a class of functions as you can. So we'll get more accurate results for a more general class of functions. Okay, but we can also get more accurate results if we're just a little bit clever about the kind of functions that we're choosing as our guess. Okay, so we also get more accurate results if we make a better guess. And just as a really simple example of that, if we think about this harmonic oscillator potential again, then it's symmetrical left and right, and so we might also think that our function should be symmetrical. And as I said last time, we have this picture classically that the particle is going to be confined into some region. If the particle has a certain energy classically, then it can't go past a certain value of x. And so there we might think that we should be looking for a function that dies off for large values of x. So we can use a little bit of our physics intuition to come up with a more clever guess for what should be our variational wave function. It's usually not possible to actually try all the wave functions, and so we have to be as general as possible, and then also use whatever extra physics input we can to make the best guess possible. In the end, it's hard to tell how close we actually are. So that's kind of the downside of the variational method, that we have an upper bound, but normally the variational method doesn't give us a lower bound. Sometimes there are other ways that we can establish a lower bound on the ground state energy. Finally, one thing you'll notice is that here we're only talking about the ground state energy of our system. Okay, so the method as we've explained it so far, it doesn't really tell us anything about what is the difference between the ground state energy and the first excited state, or what is the energy of the third excited state. There is some version of the variational method that can be used to help estimate some of these other energies as well. And I'll probably post a little bit about that, maybe just an extra article that you could read if you're interested. Okay, so we'll give you some homeworks, starting with some simple web work problems, and then I'm actually going to give you a competition. This is an annual event in Physics 402. I'm going to give you some Hamiltonian that can't be solved exactly, and I'll leave you to apply the variational method to this Hamiltonian, and whoever in the class ends up with the result that's closest to the ground state energy is going to win a fabulous prize. So you'll have to wait to see what that is this year.